All right, we're back. We're on page 2 of note 16. We're talking about parametrics and derivatives and calculus. And we've learned so far that x and y kind of like move independent of each other. So really you just kind of like deal with what is x doing? Are you moving left or right? And you deal with what is y doing? Are you moving up or down? And then sometimes we'll be combining them like we're going to do right here. We can eliminate the parameter, but that's usually not the point when you're dealing with parametrics. Usually the point is to independently look at left-right motion, up-down motion. And kind of like think about it. So here in the previous part, you should have found that x equals 4y. We definitely found that. Calculate dy dx implicitly, determine the equation of the tangent line to the curve at -3 1/2. Okay, so if x is equal to 4y squared, it was definitely not as smooth when I was writing on the iPad in the last video. I don't know if it like came across in the recording, but like it was weird. So hopefully that does not happen again. I tried to turn off all the things that were going to happen during this, all the reminders, but like, who knows? All right, we're taking the derivative with respect to x, right? So it's like d dx of x equals d dx of 4y squared minus 4. Showing more work than I should, but the derivative of x is 1. This will be 8y dy dx by the chain rule, and then minus 0. So then dy dx is going to be 1 over 8y. So you get like an implicitly defined derivative. Totally fine, right? Parametrics are a little weird, so it's not really that unusual that that would happen. So then dy dx, I'm going to do such that and put the full ordered pair. -3 1/2 is going to give me 1/4 because y is equal to 1/2. And then I want the tangent line. So the tangent line is going to be y minus 1/2 equals 1/4 x plus 3. All right, so that's my tangent line. I guess I should label it tangent line. You know, you got to make your work look how you'd want someone else's work to look. So there we go. That's our tangent line. Now let's see if we can do it a slightly different way. So we're essentially going to use kind of the chain rule. Like if I want dy dx, and then y is really a function of t, it would be like dy dt times dt dx. But then dt dx is, you know, I could be writing all this down. So I want dy dx, but y is actually a function of t. So that's really dy dt times dt dx. But really that is dy dt divided by dx dt. So it turns out that to find dy dx, all I need is dx dt, dy dt, and do dy dt divided by dx dt. It's going to work. So we're given, it's reiterated here that these are the parametrics. Really common for parametrics to be given as like an ordered pair where each coordinate is a function and then they can vary. So this is a common notation. Get used to it. Not a big deal. It's just telling us that x is t squared minus 4 and y is t over 2. We're good. So let's calculate them. I recommend that you find dy dt first. And the reason that I recommend that is people tend to just divide, they tend to divide the first thing by the second thing, like without thinking really about it. So I'm going to find dy dt first. I'm going to find dx dt. I'm going to find them vertically. And so this is 2t. So we can combine these and say that dy dx is going to be 1/2 over 2t. So I'm getting 1 over 4t. Now the question is, what's t, right? So that's the question we need to answer. Well, there's two things we can do to get it. We know that the x coordinate's -3, and we know that x is t squared minus 4. But think about that. That's a quadratic has to equal -3. There could be 2 times at which that happens. The other thing that we know is that y is going to be 1/2, and y is equal to t over 2. There's only one value of t that makes that work. So let's assume that this is a complicated situation, which it's not. But let's say that it was. We would have started with this, and we would get, I don't know, t is plus or minus 1, right? So that makes x work. X will be equal to 3 when t is positive or negative. I don't even know what I'm saying. X is going to equal 3, -3, come on, when t is plus or minus 1. I got it out, I think. So now there's two candidates, but then y, t over 2 equals 1/2. So this is for x. Well, actually, I could write x equals -3. Let's make this look good. X equals -3 gives me this. Y equals 1/2 gives me this. And this gives me that just t equals 1. So if there were two different values when y was equal to 1/2, what I would look for is what t value shows up twice. The only one that shows up twice here is 1. So we know that t equals 1. So we'll do dy dx such that t equals 1 is 1/4, which is the same answer we got here. And despite how much I stumbled through it, that's actually easier. This was easier. So we get the same value. That's kind of interesting. And it's important, and it's how we're going to actually calculate things, is by using dy dt divided by dx dt. It's very straightforward. All right, let's see. So use parametric equations, find the equation of the tangent line at t equals -1. All right, so we said, so I'm borrowing some stuff here. We said dy dx from the previous part is 1/4t. And we're being told that t is -1. So we'll just do such that t equals -1 is -1/4. And then x, we know is t squared minus 4. So x of -1 is going to be -3. And y is equal to t over 2. So y of -1 is -1/2. So our tangent line. So the biggest mistake that I see people make, and I see people make it all the time. Last year, one of my best students scoffed at the notion when I said, this is the #1 mistake people make. And then he promptly made it on the first quiz that we had. So don't be like that. People mess up and they use t instead of x, like all the time, right? The ordered pair is -3, -1/2. Make sure you're using -3 for x, not using the t value. It's the #1 mistake. Don't do it. Y plus 1/2 is -1/4, and then x plus 3. Make sure you use the x value. This is our tangent line, looking good. So that wasn't bad. All right, by looking at the curve and the table, determine, I don't know what the table would tell. Oh, I guess the table tells us t values. Determine the t intervals on which the curve is concave up and concave down. All right, let's go look at our curve. All right, parametrics, there's no such thing as like concave to the left and concave to the right. You're still just going to say concave up or concave down. So if you look at this curve right here, the tangent line would definitely be below the curve on this interval. So the curve is concave up from t equals -2 to t equals 0. Concave up -2 to 0 for t. T equals -2 to 0. It's concave up for, I don't know, you can't even really describe it in terms of x and y, like you have to use t. So -2 to 0, concave up. And then from 0 to 3, the tangent line would be above the curve, so the curve is concave down, so concave down from 0 to 3. So that's by looking at it. There is no such thing as concave left, concave right. This maybe, I don't know, feels like it should be concave to the right, perhaps. If that was a thing, that would probably be the answer, but it's not a thing, right? So we think that, I thought it was concave up for -2 to 0, and then concave down for 0 to 3. That's what it looks like. Now, we don't know how to find this yet. It's a chain rule type thing again. The second derivative I'm just going to give you is this. Notice the second derivative is -1/8t cubed. The first derivative is 1/4t. If I just take the derivative of the first derivative, I don't get the second derivative. Like the reason for that is that t is the variable, and this is dy dx. So I need to find the derivative of this with respect to t, and then I need to compensate and multiply by dt dx or divide by dx dt. We don't need to do it yet, but just know that taking the derivative of this does not give you the second derivative. It doesn't do it. So keep that in mind. Second derivative is a little more complicated, so we're going to have to work that out. And we will. But this is the second derivative. So yeah, definitely. If the second derivative is -1/8t cubed, then the second derivative is greater than 0 for t less than 0. And the second derivative is less than 0 for t greater than 0. So this is like a little weird. So it confirms concavity. Confirms our thoughts. All right, so I'm going to stop this video here because we're at the end of the page. We know that we can find the slope of the tangent line, dy dx, by doing dy dt over dx dt. We know that we can analyze the motion left and right by looking at dx dt, up and down by looking at dy dt. We can write tangent lines. When you do that, t doesn't show up in your tangent line anywhere, right? It's still just y minus y0 equals the slope and x minus x0. Don't put t in there. Biggest mistake you can make. Most common mistake. It's not the big. There are so many bigger mistakes, but that's definitely the most common. All right. I will see you in the next video.